This is part 4 of our video on equations of transformed functions. So our last question here says, transformations were applied to the function y equals x cubed to produce the following graph. Determine the transformation equation. So I'm looking at this graph, and I know, based on the different shapes of the functions that we've done, that this is not exponential, it is not logarithmic, it is not sine, cos, or tan, which means it's a power function. I can also tell, looking at it, because it has an inflection point, instead of having a vertex, it doesn't look like a parabola, that it has to be an odd degree exponent, which it is. It is x to the power of 3. So my base function that we're working with here is, let's call this g of x. So g of x equals a times, and it's a power function. So it's something to the power of 3. How do I know it's the power of 3? That was given in the question. So then there's the b times x plus h in the bracket, and then plus k. So what we would like to do is figure out what a, b, h, and k would have to equal to match that graph. Okay, trig functions, like the previous question we did, has a lot of special features, right? So the special features of our trig function, the period, the amplitude, the phase shift, and the midline, make it really easy to determine the equation. When you're dealing with power functions, it's a little bit trickier. Now, power functions do have one very special feature that would help us find parts of our equation, and that is either the vertex or, in this case, the inflection point. So there's an inflection point there where it is changing from being concave down to concave up, and this is the point 1 and -5. Now, traditionally, the inflection point on your graph would start at 0, 0. So that means that this graph has moved down 1, 2, 3, 4, 5 spaces, and it has gone right 1. So it's gone down 5 and right 1. What would move it down 5? That would be a k value of -5. And what would move it right 1? That would be an h value of not +1, but -1. It's always the opposite of what you see here. So this is actually -h and k. Okay, well, we're partway there. We've got our h, we've got our k. All I need to do is figure out whether it has been horizontally and vertically stretched, compressed, or reflected. Now, in order to do that, what we really need to do is we need to take the base function y equals x cubed, and we need to graph it. So I'm going to make myself a table of values of y equals x cubed. I'm going to plot it on the graph, and then I'm going to try to look and see if I can figure out whether the graph has been stretched or compressed. So I'm going to make myself a table of values. We have x and y. We are just doing y equals x cubed. So I'm going to pick some numbers. So I'm going to do -4, -3, -2, -1, 0, 1, 2, 3, and 4. Those are kind of the standard numbers that I normally would choose. So we're doing x to the power of 3. So -4 to the power of 3 is -64. -3 to the power of 3 is -27. You can use your calculator to help you out with this. -2 to the power of 3 is -8. -1 to the power of 3 is -1. 0 to the power of 3 is 0. 1 to the power of 3 is 1. 2 to the power of 3 is 8. 3 to the power of 3 is 27. And 4 to the power of 3 is 64. I'm going to plot as many of these as I can on this grid. So -64 is way too small. It won't fit. My graph only goes down to -12. Negative 27 also is not going to fit. But negative 2 and negative 8 will fit. Negative 1 and negative 1. 0, 0. 1 and 1. 2 and 8. And then 3 and 27, the 27 is too large. And 4 and 64, the 64 is too large. So my inflection point on just a standard x cubed would be at 0, 0. So this side is going to look like that. And this side is going to look like that. Okay, so this is where I'm going to use my eyes to tell me some things about my graph. Do I think my graph has been reflected? Right? I don't think so. If it has, it's been both horizontally and vertically reflected, so it all kind of cancels out. I don't think this is different. It has the same shape, right? It's increasing to the inflection point and increasing. It has the same pattern here. So I think that it has not been reflected. If it was going down and it was decreasing instead, then I would think maybe it had been. So then the second part I need to do is I need to figure out if it has been horizontally and vertically stretched and compressed. So the secret to doing this is to find 2 points that match on your graph. So one point that I can spot fairly easily is the inflection point, right? So that would be this point and this point. They are both the inflection points. And then I am going to choose a second point. And I think I'm going to pick the one that's to the right of it. So this point here and that point there. So this little section of curve here matches up with this section of the curve here, right? So we went from the inflection point to the first point on the right, from the inflection point to the first point on the right. And I'm going to look at horizontally and vertically how that changed. So originally this one here went over 1 and then up 1. This part here goes over 1, 2, 3, so it goes over 3 and up 2, right? So if I think about it vertically, it was going up 1, now it's going up 2. So this has been stretched by a factor of 2. 1 times 2 gives me 2. So I think this is a vertical stretch of 2. So that would make my A value 2. If I look here at my x values, we went over 1. Now we're going over 3. So this 1 has now become a 3, so that's been stretched by 3. Now horizontal stretches look a little different. They're not just going to be a 3, it's going to be a 1 over 3. So just one more quick recap of what I did. I found the inflection point because it's an easy point to spot on both graphs. And then I chose the point directly to the right of it in both cases. And then I counted to see how far over and how far up we went to get from the inflection point to that next point. And then I compared. So I saw that vertically, originally we were going up 1, now we're going up 2. So that's been doubled, right? So that's been a stretch of 2. And then going from side to side, we were moving over 1. Now we're moving over 3. That's been tripled. So we've multiplied by 3 or stretched by 3. Okay, that means my final equation here is going to be g of x equals a, that's 2, times b, that's 1/3, times x plus h. This is a minus 1, so minus 1, x minus 1, to the power of 3 minus 5. And that's my final equation. All right, and that's the end of our lesson on equations of transformed functions.